I'm just going to introduce the basics of shortest path, and it's going to form really the basis of shortest path problems in networks. And I guess where this comes from is situations such as getting from sort of one point to another, or traveling from one point to another. So for example, between home and school, or home and work, there's more than one way to get there. So you might find that the main road to get from, for example, home to work, there might be too much traffic. So you might think about taking another way, or maybe some back streets or something like that, to save the time. I mean, it might be a greater distance, but it still might, you might be able to get to work a lot quicker. So this is really about considering the cheapest way, the shortest distance, shortest amount of time, whichever way you want to look at it. That's the basis of shortest path problems. Okay, but the way we're going to start off though is that let's just consider this network here. All we're going to do is that we're just going to find the shortest path between vertex A and just every other vertex. Okay, so we're not being specific as to any particular vertex here. Okay, so what we're going to do is it's a bit of an algorithm that we're going to go through. Starting at vertex A, okay, let's consider the vertices that are closest to A, so one edge away. So we've got vertex B, vertex C, vertex D, I guess. So we can do these one at a time. So we want the shortest path, so the path from A to B. Okay, we need to consider all the various ways we can get to B. We can get to B directly, so from A to B, that's a cost of 2. We can get to B via D, so we can go A, D, B, but that's a cost of 10, so certainly that's not the shortest path. When we say shortest path, it doesn't matter how many edges we choose. It's the sum of the numbers, the sum of the weights on the edges that matters. Okay, so sometimes we fall into this trap thinking, oh, but I've taken too many edges to get from one vertex to another. That doesn't matter actually. What matters is the cost or the weight of the edges. The sum of those has to be the minimum, not the number of edges. Okay, so can you just make that one point very clear. Okay, so from path to A to B, from just by inspection. Okay, I'm just going to put the weight of the path, or the weight of the path from A to that vertex that we've chosen. I'm just going to write that up in green there. Okay, what about, say, vertex C? Vertex C, we've got a direct path there from A to C, and that's 5, or costs 5. I call it a cost, sort of a cost in time, a cost in money, or a cost in distance, or some other cost. So that's 5. We can go to C via D, but I don't think that's going to help us here, so that's 11. There's so many other ways you can get there, but some of these other paths are just ridiculous. We don't even consider them. I mean, the value that you're going to get when you add up all the numbers is going to be too high. So we just consider the most reasonable options. So A to C, well, probably just direct. A to C is just 5. Okay, so I'm just going to fill this in. So path from A to B, we get 2. Path from A to C, okay, is 5. Okay, what about D? Okay, so I'll give you a few seconds just to think about that. Okay, think about the various ways you can get to vertex D, starting from vertex A. We got a direct path, of course, that's going to cost you 7 units. We can go to D via C, so A, C, D, that's 9. But we can also go via B, so A, B, D, 2 plus 3, that's 5. So we want the shortest path. So when I say shortest path, yeah, sure, it's taken 2 edges, and 2 edges is obviously greater than 1 edge, but we don't care. Okay, so we don't count the number of edges. It doesn't matter. Just add up the values that make up that path. So from A to D via B, 2 plus 3, it's 5. Okay. So these numbers now that I've placed next to the vertices are basically the weight of the path from A. Okay, I'll just put that in a circle. From A to these 3 vertices. Okay, we've got 2 more now to consider. So what about path E, or the path to E from A? We've got 2 plus 7, so that's 9. There's another way that I can see. We could go A, D, E. Okay, that's 7 plus 1, that's 8. There's still a better way. Okay, D, to get to D only costs 5 anyway. So we can use what we've calculated before to help us find the shortest path to that vertex. It takes 5 units or a cost of 5 to get to D via B, A, B, D. Add another 1 to it. It's the smallest. It's the lowest weight edge there. So 5 plus 1 is 6. So A to E. Okay. The cost there is 6. Okay. Now finally, to get to F, okay, we can get to F via either E or D. 5 plus 8 is 13. Okay. Or 6 plus 9 is 15. So clearly 13 wins out there. So A to F, okay, is 13. So what we've done is we've calculated the shortest, basically the shortest path, or the lowest weight path from A to each of these other 5 vertices.